So into new stuff. Okay, we're just going to start with some definitions. Okay, just to kind of orient you to the language I'll be using throughout the next couple chapters. So molecular recognition, like I said, we're talking about binding. The specific binding between some molecule and another molecule, and they're forming a non-covalent complex. Non-covalent is sort of the key word here. What did that mean? What were our non-covalent types of interactions? No, ionic interactions, not the same as an ionic bond, but something like a salt bridge. So there's like permanent charge that is forming some attractive interaction. We talked about hydrogen bonds. We talked about hydrophobic interactions. The only one that was a true covalent bond, but we still counted it sort of under this, was the disulfide linkage between cysteines. Okay? So the two molecules that could be interacting are a protein and another protein or a transcription factor binding to a DNA strand. And the one we'll talk about most is protein binding to a ligand. So a ligand is just any sort of small organic molecule that is going to bind to just a larger molecule. Okay? It's the small part, and the protein is the macromolecule, or the big part. What are any, besides a drug, what are some other examples of ligands? Or ligands, whatever. Yes? Steroid hormones, great. Neurotransmitters, perfect. Neurotransmitters, cytokines, growth factors, toxins, hormones. I don't have water. All of that is good. Okay? Yep. Antibodies and antigen interactions. There's a figure that'll pop up with that. Okay, so then some of these interactions might be hydrogen binding, ionic interactions, hydrophobic interactions. The ligand is our small organic molecule binding to the bigger molecule. And in this case, this bigger or macromolecule, we're generally going to have just like the lump sum term, it's the receptor. So the protein that the drug is binding to is the receptor for that drug. Okay? For today's class, we're talking about one ligand, one receptor, sort of the most simple case, one-to-one binding. Obviously, real life is that any given receptor, any given protein or DNA can bind a lot of things, and when one thing binds, it influences how everything else can bind. So allostery or allosterics, when the binding of one ligand is regulating the binding of others. This will be the chapter 14, so probably next Wednesday. This is a chapter that didn't used to be included 2 semesters ago, and I put it back in because I think it's interesting. Oh, there's nothing else on that slide. Okay, so we'll get to that. More definitions. So when these two things actually bind to each other and form their complex, and then you put them into solution at room temperature, you expect them to, some amount of them to come back apart and dissociate. Okay? And so actually in solution, what you're having is if you have your protein or your receptor, whatever it is, and your ligand, your drug, your hormone, whatever that is, these things are actually associating and dissociating actually pretty rapidly and pretty frequently in real life. Okay? If you don't have a concentration, if you have a very, very, very high concentration of ligand, all the receptor will be bound. And if you don't have any ligand around, none of the receptor will be bound. And generally, the binding is what initiates some downstream cascade in your body that does something of interest. So if you're not at concentrations where they can sort of associate and dissociate pretty regularly, you're either like turning something on always, which is usually bad, cancer, or you're turning something off always, also bad. Okay? So you're going to have this mixture of sort of bound and unbound, or the other way that you'll see unbound listed on the slides throughout is free. So you'll have bound and free molecules at an equilibrium. And relative concentrations of the bound and unbound molecules kind of let us determine the strength of the interaction. So if something is really strong, you'd expect all of it to be bound up. If there's a really strong binding interaction, alternatively, if you see a lot of unbound or free molecules, you would expect maybe that interaction not so favorable, not so strong. Okay? And we will look at this, we will relate it to the way our equilibrium constant looks. Okay. So the word affinity. Affinity is the strength of interaction between the two molecules. the greater the decrease in free energy upon binding, the greater the affinity, okay? So it's kind of a confusing language, but when these two things come together and bind, okay? So if we model it like a reaction, here they are, they're reactants, they haven't bound. Over here, the product is they're bound. If in that forward direction of binding, delta G is really, really negative, that is a really favorable binding interaction. It wants to happen. They have high affinity for each other. So like I said, when you see the words high affinity, delta G of binding is very, very negative. And alternatively, if you do not, if you have a positive delta G, then unbinding is favorable. It would go back the other way. Okay. And then specificity, which will be Monday's conversation in chapter 13, is talking about relative strength. Okay? So certain ligands will have preference for a given receptor over others, and you can sort of have comparison of these different affinities, and that's where we get into specificity. And thus, the way this relates to free energy change is that, again, then the free energy change of binding will be more negative for whatever the favored ligand is. Whatever has higher affinity is going to have this lower delta G. And I will just say, watch the subscripts, because not necessarily to trick you, but if this says unbinding, then you're now looking at the other reaction in sort of the reverse direction, and your signs would flip. So just pay attention for which reaction you're being asked for. Are you asking for when things are binding or when things are unbinding from each other? Okay. And so then here are just some visual examples from your textbook. You could have the two strands of DNA coming together would represent, duplexing DNA would be molecular recognition, transcription factor binding to DNA, an enzyme binding to its substrate. So substrate is just the name for the specific ligand that an enzyme is specific to. We could have an enzyme binding to a drug, though. We could have a hormone coming in, attaching to some surface receptor or membrane receptor, and antigens and antibodies are also an example. Any